Hey there. Subscribe to my channel. And also press this bell icon, so you never miss any new updates, cause whenever we upload new video you will get a notification on your phone.
Okay students, in the previous class we discussed how to find out the numbers between any two given rational numbers. Okay, so we solved many examples that how to find out the rational numbers between any two given numbers. So let me solve the exercise 1.2. okay, say that, see the first one, the statements are given there. We'll have to just justify whether it is true or false. If it is true, we'll have to justify. If it is false, then also we'll have to justify our answer. Okay, let me say, state whether the following statements are true or false, justify our answer. So in the first main, we got the first one. Okay, the statement is given, every irrational number is a real number. Every irrational number is a real number. Look at the statement. Say as said, every irrational number is a real number. Okay, see, we know what is real number. Okay, we know the real numbers include rational and irrational numbers. Okay, say real numbers means including the rational as well as the irrational number. We call that set of numbers as the real number. So look at the statement, every irrational number is a real number. Means real numbers is nothing but it's a group of rational as well as irrational numbers. For example, real numbers, if I take, for the rational numbers, if I take A, and irrational numbers, if I take B, including both the numbers, it is called as the real number. Real numbers means including the rational as well as the irrational. If you look at the statement, every irrational number is a real number. It means in the group of real numbers, every irrational number lies. So the statement given above is true. It is. Okay, the given statement is true because, see, because real numbers include rational and irrational numbers. Each and every irrational, it is a member of real numbers. So the statement given is true. Okay, so let us look at the second statement given there. See, what is the second statement? Every point on the number line is of the form root m. Okay, say the statement is given, every point on the number line is of the form root m, where m is a natural number. See, if you look at a real number line. See, this is the origin O. So on the right side of the 0 there are positive integers, as you know. Okay, so on. Okay, on the left hand side there are negative numbers, -2 and -3, so on. Okay, if you look at the statement, it is said that every point on the number line is of the form root m. See, every point, according to the statement, every point, okay, these are the points, every point on the number line, they are of the form root m. But if you look at these numbers, positive integers, here some are negative integers are there, they are not in the form root m. You can take any of the, if you take this point, it is 2, which is not equal to root m, or it is not of the form root m. Okay, if you look at -3, it is also not of the form root m. Okay, So the statement given here, every point on the number line is of the form root m, is absolutely wrong it is. So the given statement is false it is. False. What is the reason? How to justify? The every point on the number line, it is not of the form root m. Okay? So the statement given is false it is. Okay? The false statement. So let me check the third one. See, look at the third one. The third statement is given. Every real number is an irrational number. Every real number is an irrational number. See, this third statement, it is nothing but the vice versa of the first one that just we solved. Okay? So look at the first statement given. Every irrational number is a real number. If you look at the third statement, every real number is an irrational number. As I told you, real numbers, okay, these real numbers, they include rational numbers plus irrational numbers. Rational plus irrational. Okay? Real numbers include rational as well as irrational. If I say every real number is an irrational number, it becomes false because real numbers include rational as well as irrational. Real number, it is not just only a group of irrational numbers. It's a group of rational as well as irrational. That's why the above statement given is false it is. Okay, because every real number is not irrational. Okay, a real number either it is rational or irrational. So we can say every irrational number is a real number, or we can say every rational number is a real number. These statements are true. But if we say every real number is an irrational number, it is false. Okay, say. In that the second main is also given. Say, look at the second main question there. Are the square roots of all positive integers irrational? If not, give an example of the square root of a number that is a rational number. Say, are the square roots of all positive integers irrational? If you look at the square roots of the positive, square roots of the positive integers. For example, if you look at 4, it's a positive integer. Okay, what is the square root of 4 here? As you know, it is 2. Okay, but in the statement we have asked, are the square roots of all positive integers irrational? If not, give an example of the square root of a number that is a rational number. If you look at 4, it is a rational number. Or take another example, 16. 16, it is a rational number because it is in the form p by q, where p is not equal to 0 because it is having the denominator as 1. Okay, so we can say this 16 is a rational number. We'll have to check its a square root. If you look at the square root of the 16, if you look at the square root of 16, it is nothing but 4, which is not an irrational number. Say, so we can say that the square roots of the positive integers are not always irrational. It is because it's a natural square root we got, which is the square root we got here, it's a natural number. That's why the statement given here it is false. Okay, it's a false statement. Okay, that's why the square roots of all positive integers are not always irrational. Okay, say in the next class we will go for the decimal expansions of the real numbers. Okay.